Here we have question 2, and the first question define heat thermal capacity. So this heat thermal capacity is the amount of energy required to raise the temperature of an object, it can be any object, by 1 degree Celsius or Kelvin. So we're looking at, we're not looking at per kilogram as the small c here. The small c is your specific heat capacity, and that is looking at the amount of heat required to raise the temperature of 1 kilogram per 1 Kelvin. So the heat capacity is purely just looking at any object. So you could take anything, and you could take, for instance, your coffee mug, and you could work out what the thermal capacity of this. How much energy will it be required to raise that coffee cup by 1 degree Celsius? Obviously, you would use the idea of an object or a substance. So now we get a question here. It says a piece of metal is held in a flame of a Bunsen burner for several minutes. The metal is then quickly transferred to a known mass of water contained in a calorimeter. Now, I just want to highlight two words here, or two points here. Firstly, this idea of quickly. So we take this piece of metal and we put it in quickly in there. Obviously there we're going to assume that we're not losing any heat in that process because we're doing quickly. If we did very slowly, it would lose some heat. And then it's held in the Bunsen burner for several minutes. So therefore we can assume that the temperature of the flame, that temperature is equal to the temperature of the metal. Okay, so we're going to use that. So here we've really explained this. The metal is transferred as quickly as possible. This is to avoid heat loss in the transfer. And the water is stirred. This is to ensure, because we're measuring the temperature here. We're measuring the temperature. So this is to ensure that the water reaches a constant temperature throughout the liquid. Alright, we don't want just a pocket of hot water over there, and then we maybe are measuring the temperature over there. So we stir it so that the temperature that we're to be measuring is actual measure of all the temperature of the temperature of the whole thing. Okay, going over the page, we're going to do a calculation here. Now we have this. It says the following data are available. The heat capacity of the metal is equal to that. The heat capacity of the water in the calorimeter is that. The heat capacity of the calorimeter is that. The initial temperature of the water and the final temperature of the water. Now we would assume that the calorimeter has also got these temperatures. So we're basically going to get a heat loss. We're going to get Q loss is equal to Q gain. Now the loss is going to obviously come from the metal, and this gain is going to come both to the water and to the calorimeter. Now it says in the question here, assume negligible energy losses in the process involved. Use the data to calculate the temperature T of the Bunsen burner. So, what was the loss for the heat? Now, for every Kelvin change, there's 82.7 joules of energy. So, we're going to have 82.7, and that the change in temperature for that. Now we know that the final temperature of the water is 353, and because the metal was put into that, we would assume that the final temperature of the metal was also 353. So your initial temperature minus 353 will actually give you the change in temperature for the metal, and therefore when we multiply that by 82.7 we'll get the heat that was lost by the metal. Now the gain for the water, we have here that the heat capacity of the water is 5.46 times 10 to the 2, so 546. 546, and the temperature increase, it went from 288 to 353. That's going to be an increase of 65. Is that correct? 65. So we're going to times that by 65. So every degree we need to add 546 joules, and then plus for the calorimeter, that's 54.6 joules. So that's 54.6, and that's also times 65. That's the amount of energy that will be required to raise the H2O, the water, and this is for the calorimeter. And this is the energy from the metal. Alright, so we've got to solve this. Now I hope you won't have any trouble in solving this. You get a temperature, final temperature when you do this, of 825 Kelvin. I will leave that calculation to you. If anybody needs help with doing this, please come and see me.